Take a look at 3I Atlas once again, as this interstellar object has surprised the scientific community yet again through observations of its tail. Unlike any comet recorded before, the massive anti-tail of 3I Atlas forms a needle-like structure that points straight toward the Sun. This is not a visual illusion or a trick of perspective. The structure is so large that its length rivals the distance between Earth and the Moon. And that is not all. Spectral data reveals strong traces of nickel, while iron, an element that normally appears alongside nickel in nature, is nearly absent. This combination of never-before-recorded differences has turned 3I Atlas into one of the most mysterious and closely watched objects in modern astronomy. Join MindGap as we follow the journey of 3I Atlas and explore the strange behaviors this object continues to reveal. Three I Atlas is the third confirmed interstellar object ever observed passing through our solar system. Unlike asteroids or comets born around our Sun, this object formed around another star and traveled through interstellar space for millions of years before reaching us. Its path is hyperbolic, meaning it is not bound by the Sun's gravity and will never return. That alone already makes it rare, because most objects we study belong to our own cosmic neighborhood. When astronomers first detected 3I Atlas, they expected a familiar pattern. If it behaved like a normal comet, it would slowly brighten as it approached the Sun and form a tail that streamed behind it. That expectation comes from decades of observation and well-tested physical laws. Those laws describe how ice turns into gas, how dust is released, and how solar radiation pushes that material outward. For most comets, this process is predictable and consistent. Only after this context does the real shock of 3I Atlas appear. As telescopes focused on the object, scientists noticed something that did not fit the model. Instead of a tail flowing away from the Sun, a long and narrow structure appeared to point in the opposite direction. This feature looked like a sharp needle extending forward, straight toward the Sun. At first glance, some assumed it was an anti-tail created by geometry. In astronomy, an anti-tail usually forms when Earth crosses the orbital plane of a comet. From that angle, dust that is actually trailing behind can appear reversed. This effect has been seen before and is well understood. The key point is that such an illusion changes quickly as viewing angles shift. With 3I Atlas, that expected change did not happen. The forward-pointing structure remained visible across different observations and positions. It did not flip back or fade as Earth moved along its orbit. Instead, it held a consistent orientation that suggested something physical, not visual. Measurements showed that this structure stretched tens of thousands of kilometers into space. Some estimates placed its length close to the distance between Earth and the Moon. For any comet, that scale is extreme. To understand why this is so troubling, we need to return to basic physics. Once dust leaves a comet's surface, sunlight immediately begins to push it away. Even large grains feel this pressure and slowly drift backward. Charged particles behave even more strongly as the solar wind sweeps them away at high speed. This is why comet tails always point away from the Sun. There are no known natural conditions where dust or plasma can remain steadily oriented sunward for long periods. That is why the anti-tail of 3I Atlas is not a small detail. It challenges the core assumption of how material behaves in open space. Comparisons make this contrast even clearer. Well-known comets such as Comet Lemon developed broad and bright tails after passing close to the Sun. Those tails expanded outward and became more dramatic with increased heating. In images of 3I Atlas, the rear side looks faint and disorganized by comparison. There is no dominant trailing tail that matches what we see in typical comets. Instead, the most prominent structure is the one that should not exist. Scientists have proposed several explanations, but none fully resolve the issue. Some suggest unusually heavy dust grains that resist radiation pressure. Others argue that focused jets could temporarily overpower solar forces. Each idea explains part of the observation, but fails to explain its stability and scale. This is where the real tension begins. If the basic rule about comet tails no longer applies here, then other assumptions may also need revision. That does not mean 3I Atlas is artificial or unnatural. It means our current models may not be enough, and once a foundational rule breaks, every conclusion built on it becomes uncertain. So the anti-tail is not just a strange shape in the sky. It is the first signal that 3I Atlas may be operating under conditions we have never tested before. If its tail can defy solar forces, what else about this object might defy expectation as well? And as scientists look closer, a new question begins to emerge. Is this object chaotic and unstable, or does it show signs of order beneath the mystery? One of the most overlooked aspects of 3I Atlas is not how strange it looks, but how controlled its behavior appears to be. At first glance, an interstellar object should behave like chaotic debris, shaped by random forces and unstable reactions. After all, 3I Atlas has traveled through deep space for millions of years before entering the influence of our Sun. Many scientists expected irregular activity, uneven outgassing, and unpredictable changes in structure. What they observed instead was something far more organized. Repeated observations show that the anti-tail and related jet structures do not appear randomly. They shift direction in a smooth and repeatable pattern over time. This motion follows a clear cycle rather than sudden bursts or erratic swings. That pattern points directly to rotation. By tracking how the direction of the anti-tail changes, researchers were able to estimate the rotation period of 3I Atlas. The result suggests a spin cycle of roughly 7 to 8 hours. For an object of this size and origin, that is both fast and remarkably stable. Even more striking is what this rotation tells us about the object's internal structure. A stable rotation requires balance. If the body were loosely bound rubble, uneven mass would cause wobbling or tumbling. Instead, the data suggest a well-organized shape with a consistent spin axis. This matters because the direction of the anti-tail appears closely linked to that axis. Rather than spraying material in all directions, 3I Atlas seems to release material in a controlled way. The jets remain aligned with its rotation instead of breaking apart. This is not typical behavior for an active comet. In most comets, jets switch on and off as different icy patches rotate into sunlight. That process creates chaotic and short-lived structures. With 3I Atlas, the changes are smooth and predictable. The anti-tail does not vanish between cycles. It shifts gently, as if guided by the object's internal motion. This level of coordination suggests that the structure producing the tail is persistent. It is not just a temporary reaction to sunlight. Some researchers argue that this points to a single dominant source region rather than many random ones. That region appears to stay illuminated for most of the rotation cycle. This could explain why the jet remains active even when the object's orientation changes. It also raises new questions about the composition and geometry of the nucleus. A stable spin axis also makes the scale of the anti-tail harder to dismiss. Maintaining such a long structure requires consistent output over time. Short bursts would fade quickly under solar pressure. What we see instead is continuity. This stability becomes even more interesting when considering image quality. Some of the most debated images come from instruments with limited resolution. Low detail makes it difficult to measure exact angles and boundaries. Even so, the overall pattern appears again and again across different observations. That consistency reduces the chance that this is a measurement error. It suggests a real physical process at work. This is where the story begins to shift. This shift changes how scientists frame the mystery of 3I Atlas. The issue is no longer limited to strange shapes or unusual chemistry. The object shows signs of internal balance, stable rotation, and sustained activity that does not behave like loose or fragile debris. That level of physical order suggests a body capable of maintaining controlled processes over time. Once that possibility is accepted, attention naturally moves away from how 3I Atlas looks and toward when its activity began, because stability alone is not enough to explain why this object was already active long before it reached the inner solar system. And that early behavior opens a new layer of the mystery, one that starts far from the sun itself. One of the least discussed but most revealing traits of 3I Atlas is how early it began to show signs of activity. Long before it approached the inner solar system, telescopes detected changes that suggested gas and dust were already being released. At those distances, sunlight is weak and scattered, delivering only a fraction of the energy felt closer to the sun. For most comets, this level of solar input is not enough to trigger visible reactions. They remain dark, frozen, and inactive, sometimes for decades or even centuries. This behavior is so consistent that astronomers treat it as a baseline expectation. Comets usually begin to wake up only when they cross specific thresholds. As they move inward, water ice starts to sublimate, releasing gas that drags dust outward and forms a visible coma. That process accelerates rapidly near perihelion, where heating becomes intense. Before that stage, activity is typically minimal or non-existent. 3I Atlas did not follow that pattern. Archived observations suggest that it showed measurable activity while still far beyond the orbit where water-driven sublimation normally begins. This was not a sudden flare that vanished after one observation. The signs persisted, indicating a sustained process rather than a brief anomaly. For an interstellar object, this is especially striking. Unlike native comets, 3I Atlas had never been warmed by our sun before. Its surface should have been deeply cold and stable, yet something was already pushing material away from the nucleus. To explain this, scientists turned to composition. If water ice cannot drive early activity, then more volatile substances must be involved. Certain ices can sublimate at much lower temperatures. Carbon dioxide and carbon monoxide are prime examples. These compounds can become active far from the sun, where water remains frozen solid. Spectral observations later confirmed that carbon dioxide played a dominant role in 3I Atlas. This fits the idea that the object carries a chemical makeup unlike most comets in our system. However, composition alone does not tell the full story. Even volatile-rich comets from our solar system rarely show such clear activity at comparable distances. The early response of 3I Atlas suggests either an unusually high concentration of these materials or a structure that allows them to escape easily. One possibility is a surface that lacks a thick insulating crust. Many comets develop a hardened outer layer over repeated passes near the sun. This layer traps volatile material beneath it, delaying release. 3I Atlas, having never experienced such heating cycles, may lack that barrier. Its interior could be exposed and reactive. Another explanation considers internal pathways. Cracks, fractures, or porous channels could allow gas to escape without needing strong external heating. If such structures exist, they would support sustained outgassing even under weak solar energy. This idea aligns with later observations of organized jets and stable motion. Early activity also affects how scientists interpret everything else about the object. If 3I Atlas was active from far away, then the forces shaping its appearance have been acting for a long time. The anti-tail and jet structures did not emerge suddenly near the sun. They may have developed gradually, influenced by internal conditions rather than solar intensity alone. This changes the timeline of the mystery. Instead of reacting to our sun, 3I Atlas may be revealing properties it carried long before it arrived. That makes it less of a temporary visitor and more of a messenger. Its behavior offers a glimpse into environments beyond our solar system, places where different temperatures, pressures, and chemical balances shaped its formation. In that sense, early activity is not just unusual, it is informative. It tells researchers that the object does not rely on the same triggers as familiar comets. It also suggests that its internal chemistry and structure are tightly linked. This realization shifts the focus again. Once scientists accept that 3I Atlas can remain active under weak solar influence, attention naturally moves to what exactly is being released. Because the gases escaping from the object hold direct clues to where it came from and how it formed, and that leads directly into the next layer of the investigation, where chemistry begins to dominate the story. One of the most debated findings about 3I Atlas comes not from its shape or motion, but from what appears in its chemical signature. Spectral observations revealed strong signals associated with nickel in the gas surrounding the object. At the same time, iron, which is normally expected to appear alongside nickel, was barely detected. This imbalance immediately drew attention because it contradicts a basic expectation of cosmic chemistry. In most natural environments, nickel and iron form together. They are forged in the same stellar processes, especially during supernova explosions. When massive stars collapse and explode, these elements are created and scattered together into space. As a result, rocks, dust, and small bodies across the universe tend to contain both. Finding nickel without iron is therefore not impossible, but it is highly unusual. For comets, the puzzle becomes even deeper. Comets are thought to preserve primitive material from their birth environments. Their chemistry usually reflects a mix of ice, dust, and metals inherited from the early stages of a star system. In those mixtures, iron is typically more abundant and easier to detect than nickel. With 3I Atlas, the opposite appears to be true. Scientists were careful not to jump to conclusions. They began by exploring known physical and chemical explanations. One leading idea involves a compound known as nickel carbonyl. This molecule can form when nickel binds with carbon monoxide under certain conditions. Nickel carbonyl is volatile and can exist as a gas at relatively low temperatures. If present, it could explain why nickel appears in the coma even when solid metal grains are scarce. Iron does not form an equivalent compound as easily. That difference could cause nickel to escape while iron remains trapped in solid form. Another explanation considers how sunlight interacts with the surface. Photochemical reactions can selectively release certain elements. Ultraviolet radiation may break specific bonds and free nickel-bearing molecules more efficiently. Iron, by contrast, may stay locked inside minerals that require more energy to break apart. There is also the issue of detection limits. Iron lines can be harder to identify in certain observational conditions. They may exist in forms that do not emit strong signals in the wavelengths being measured. This means iron could be present but effectively hidden. Each of these explanations reduces the mystery, but none fully resolves it. What makes the situation more complex is the broader context. The nickel signal does not appear as a weak trace. It stands out clearly against background measurements. That suggests the process producing it is efficient and ongoing. If nickel release were rare or accidental, the signal would likely be faint. Instead, it appears persistent. This persistence forces researchers to consider deeper structural factors. If nickel-bearing compounds are escaping easily, the internal composition of 3I Atlas may differ from familiar bodies. It may contain layers or regions enriched in specific materials. These regions could have formed under conditions unlike those in our solar system. Different stellar environments produce different chemical ratios. Some protoplanetary disks are richer in carbon-based compounds. Others experience temperature gradients that separate elements more sharply. An interstellar origin increases the range of possible formation scenarios. This is where interpretation becomes sensitive. Nickel without iron does not automatically imply artificial origin. Nature is capable of producing rare combinations under extreme conditions. However, it does signal that standard comet models may be incomplete. Most models are built using solar system examples. 3I Atlas may fall outside that framework. The responsible scientific position is caution. The data point to a real anomaly, not a measurement error. At the same time, the anomaly remains open-ended. It invites further observation rather than firm conclusions. What matters most is how this chemical oddity fits with other behaviors. Early activity, ordered motion, and unusual structure all suggest an object shaped by uncommon processes. Nickel without iron adds another piece to that pattern. It strengthens the idea that 3I Atlas formed in a chemical environment very different from our own. As more data accumulate, the focus shifts again. Understanding composition alone is not enough. Researchers must now examine how these chemicals interact with the object's overall makeup. That shift naturally leads toward the role of dominant gases and what they reveal about its true origin. One of the clearest chemical signals from 3I Atlas is the dominance of carbon dioxide over water. This matters because water is usually the main driver of activity in comets from our solar system. As comets approach the Sun, water ice heats up, turns into gas, and creates the bright coma and tail we expect to see. That process defines how most comets behave and how astronomers predict their evolution. With 3I Atlas, the balance looks very different. Spectral data show that carbon dioxide plays a leading role, while water appears weak or limited. This reversal immediately suggests a different formation environment. Carbon dioxide sublimates at much lower temperatures than water ice. That means it can become active far from the Sun, where water remains frozen solid. This detail helps explain why 3I Atlas showed activity at extreme distances. It also explains why its behavior does not change dramatically as it moves closer inward. In many solar system comets, activity ramps up sharply near perihelion. Tails grow broader, brighter, and more chaotic as water-driven outgassing increases. Comet Lemon is a good example of this pattern. After passing close to the Sun, it developed a massive and clearly defined tail stretching far behind it. That tail expanded rapidly and followed the classic comet model. Images of 3I Atlas show something very different. The rear side remains faint and poorly developed. There is no wide, luminous tail spreading outward from the Sun. Instead, observers report a dim, smoky structure that lacks strong definition. This muted appearance matches a scenario where water is not the dominant force. Carbon dioxide-driven activity produces less dust and a thinner coma. It also creates outflows that look softer and less dramatic in visible light. This chemical balance also points to where 3I Atlas may have formed. Regions far from a star are colder and favor the preservation of carbon-rich ices. In those environments, water ice remains locked away, while other volatiles dominate surface activity. Some protoplanetary disks show exactly this kind of chemical layering. Bodies forming there would inherit a composition unlike anything common near our Sun. Because 3I Atlas is interstellar, it likely formed in such a distant zone. Its chemistry may reflect conditions that our solar system rarely produces. This idea aligns with its early activity and unusual tail structure. Carbon dioxide-driven outgassing is more stable over long periods. It does not surge and collapse the way water-based activity often does. That stability could help maintain consistent jets and structured outflow. It may also reduce surface erosion, allowing the object to retain its shape. This could explain why 3I Atlas appears physically ordered rather than fragmented. The absence of a strong water signature also limits certain explanations. If water were abundant, thermal cracking and rapid changes would be expected near the Sun. Those effects are not strongly observed. Instead, the object behaves as if it is insulated from sudden thermal stress. That again points to a different internal makeup. Carbon dioxide dominance does not make 3I Atlas artificial. It makes it unfamiliar. Most comet models are tuned to water-rich bodies from our own system. Applying them directly to an interstellar object introduces bias. 3I Atlas forces researchers to expand those models. It reminds us that the universe builds objects under many different conditions. What appears strange to us may be normal elsewhere. This realization tightens the overall picture. Early activity, structured motion, unusual chemistry, and muted tails all point in the same direction. They describe an object shaped by an environment unlike the one we know. As this pattern becomes clearer, attention shifts again, not toward new data, but toward how information about 3I Atlas is shared and interpreted. Because the more unusual the object appears, the more noticeable the gaps in explanation become. As evidence around 3I Atlas continues to accumulate, one issue has become increasingly difficult to ignore. Despite being only the third confirmed interstellar object ever observed, detailed public discussion about it remains limited. This is unusual for an object that challenges so many established expectations at once. Most scientific updates have focused on basic tracking and reassurance rather than deeper analysis. That gap has allowed speculation to grow. When information is incomplete, theories naturally rush in to fill the space. Some of these ideas stay within known physics. Researchers have proposed that the strange structures could come from highly focused jets or from an unusual internal layout. Others suggest that the object may be fractured, exposing layers with very different chemical properties. These explanations remain grounded in natural processes, even if they are rare. At the same time, more controversial interpretations have emerged. A small but vocal group argues that the organized motion and chemical anomalies resemble engineered behavior. They point to the apparent stability, the forward-facing structure, and the selective release of materials. From this view, 3I Atlas could contain or mimic technology rather than acting as passive debris. It is important to draw clear boundaries here. No direct evidence supports an artificial origin. No signals, structures, or patterns conclusively point to intelligence. These theories exist because multiple anomalies appear together, not because any single observation proves intent. This distinction matters. Science advances by questioning models, not by replacing uncertainty with belief. Responsible researchers acknowledge what is unknown while resisting premature conclusions. At the same time, avoiding difficult questions does not serve understanding either. 3I Atlas sits at the edge of current knowledge. Its behavior exposes limits in how we classify and interpret small bodies. The debate surrounding it reflects that tension. Until more data arrive, disagreement will continue. What remains clear is that 3I Atlas has forced scientists and observers alike to confront how little is truly known about objects born beyond our solar system. 3I Atlas challenges astronomy not because of one strange feature, but because of a pattern that refuses to align with familiar models. Its sunward anti-tail, early activity far from the sun, stable motion, and unusual chemistry all point to an origin shaped by conditions unlike our own solar system. None of these clues offer final answers, but together they reveal clear limits in current understanding. 3I Atlas reminds us that interstellar visitors are not just rare sights, but critical tests of what science truly knows.